Welcome to another great video. Right, so this one is specifically for grade 11 physics, and in this particular example we are tackling a NSC past exam question, sorry. So this one is from a May-June paper. You can just access it on the government's website, the department's website. So it was question 2 on this paper at least, and we were given this problem where you have two blocks, A and B, and then B is held stationary at this height initially. So what does that mean? It means that block B, right, it is not stationary because of the mass of A or the weight of A. Let's say weight, because mass doesn't really matter now. It's not stationary because of this guy, but someone is holding B initially. Because if you check, even the diagram is saying B is bigger than A, so there's no way B is being held in position by A. You will see shortly why this is important, right? So they are telling us here it's initially held at a height. So someone is holding it. We don't know who it is, we don't care. But someone is holding it. It's not being held or being balanced by the weight of A. Okay. And then it is initially stationary, or A is initially stationary on the ground as shown in the diagram below. The statement continues. When block B is released, so this person, whoever is holding it or whatever object is holding block B, they start releasing block B. Boom, they let it go. So it moves vertically downwards and strikes the ground with a velocity of 3.41 meters per second. So let's interpret this problem, right? What does it mean? It means our initial velocity, let's call it V initial. No, we usually call it VI. VI simply means V initial, ne? We'll call it VI was 0 meters per second. Why? Because it was initially stationary. Stationary, rest, and so on means it is not moving at all. Those keywords mean that. And then we are told that when it's released, it reaches the ground at a velocity, let's call it our final velocity, of 3.41 meters per second. See, now we're just collecting data. We haven't even started solving the problem. Right. So we have those two pieces of information. Of course, we're given the mass of the block and so on. So let's go ahead and check they're telling us ignore the effects of friction. So this is an isolated system. Okay. So now we're at 2.1. Show by means of a calculation that the magnitude of the acceleration of block B was 3.88 meters per second while the block was moving vertically downwards. So they are giving us a constant value. So we know for a fact that acceleration in this whole system is constant. As soon as you think constant acceleration, something in you must click. There's a set of equations that we use whenever we are concerned with an object that is moving at constant acceleration. We call that set of equations the equations of motion, right? If you remember them very well, there's 4 of them. I won't list all of them here, but we'll use the one that's applicable to this situation. And then, yeah, they're telling us, or they're asking us rather, to show by means of a calculation. Let me come this side. Right, let's show. Let us show. So remember, we had our VI and VF, right? And if you remember, once we're given those two pieces of information, we go to a list of our equations of motion. Let me show them here. Right, so you will always be given this set of equations, right? So this is from the same past paper where I got this problem. So now you come and check here, which variables do you have and which ones are you looking for? And then you would know which equation to use. So now we have VI, we have VF, VI, VF. We don't have time, so we can't use this equation to find A, right? We have VF, we have VI. We have, or we don't have A, that's what we're looking for. And we have delta X, but in this case, it's delta Y because this thing is moving along the Y-axis, or it's moving vertically. So when it's moving vertically, we use this equation. When it's moving horizontally, we use this equation, right? The difference is the delta X and the delta Y, which means either vertically or horizontally, right? So we can use this one. So we can say VF squared is equals to, we can say VF squared is equals to VI. Right, now we have this, and then what we can do now is start solving. We're given VF, we're given VI. Let's substitute. Right, so we have substituted our values. We also have delta Y, which is this distance. That's our delta Y, right? The distance it travels from whatever height, or 1.5, from the height at which it was held until it hits the ground. It's 1.5 meters, okay? Now we can divide both sides by 1.5 and find our answer. We find that A, if you want, you can just say 3.41 squared over 2 times 1.5. You know, we divide both sides by 2 times 1.5. If you remember your maths and making things subject of the formula. This gives me 3.88 meters per square second. Right, so this is my constant acceleration. Let's check if it looks like what we were asked to prove. And of course it does. So we can be sure that our answer is correct. So why didn't we use Newton's second law of motion to solve for this problem? Because we don't have so many of the variables that we would need. We don't have the tension, which we would need. For instance, let me show. So we don't have tension. We don't have. Then if we substitute and calculate weight, okay, we would have that. And then we also don't have acceleration, which we are asked to find, right? So just because we don't have this tension, it would make it an issue to use these equations to find our acceleration, right? Because now we would have to solve for t simultaneously, because this, let's say, would be block B. This would be an equation for block B. And then we would have to find another equation for block A, but block A also doesn't have mass. So we'd have to solve for the mass of block A. And remember, this was just a 3-mark question, okay? So that's why we couldn't use the Newton's second law of motion to calculate or prove the acceleration is 3.88 meters per second, okay? So question 2.2, we are asked to draw a labeled free body diagram showing all the forces acting on block B immediately after it was released. Okay, so let's focus on block B. If we go to block B, this is block B. After it was released, let's draw it here. It has the string. String always has tension, especially if there's a weight on it or some force being applied on the string. And then it has the block's weights. Let's call it WB. Weight B. You can call it WB or just W. Some people call it FG. It's up to you. Or whatever your teachers have taught you, okay? We'll use that convention that you are used to. So I'll call it WB for my case. Right, you have this. But this is a force diagram. They want a free body diagram. This is a box diagram, sorry. So let's use a free body diagram. You'd have T, and you'd have the weight, WB. As soon as this thing is released, that's what you would have there. Okay, so yes, this is your 2 marks. Then we are asked to state Newton's second law of motion in words. Well, I won't write it, but it basically says, you have to memorize this from your exam guideline. It basically says that Newton's second law of motion, right, when a force, right, is applied on an object, in a nutshell, when a force is applied on an object, that object will accelerate in the direction of the force with an acceleration that is directly proportional to the force but inversely proportional to the mass of that object. That's what it says. So if you apply 50 newtons to a car, it will accelerate in the direction of that 50 newtons. If you remember vectors, if I apply 50 newtons to the left, the car will accelerate to the left with whatever acceleration. And the acceleration will be dependent on the force that I have applied and also on the mass of the car. So it will be inversely proportional to the mass, but directly proportional to the force being applied on the car. All right, so that's what the law basically says. I won't write it now because it's something you probably can sing at this stage, okay? So now we have 2.4. So before we continue, if you check my 2.2 where I draw my free body diagram, notice that the vector representing t and the vector representing w are not the same length. Why? Because this thing is accelerating downwards, which means whatever force is pulling it downwards is greater than the force that is trying to pull it upwards. So weight is pulling the object downwards, and then the tension which is trying to pull the object upwards is actually lesser compared to that weight. That's why always be mindful of everything that you draw or calculate in physics. It means something. Don't just do it out of habit. You must always interpret it. Otherwise, it's meaningless. You're just doing something that you don't even have an idea of. Okay, so that's one thing I wanted to know. So let's go to our 2.4. So they explicitly tell us to apply Newton's second law on each block and then find the mass m, which is unknown. Okay, let's do that. But before we do that, we already have the free body diagram for block B. What about the free body diagram for block A? It will most likely look the same, right, once this thing is in motion. So let's draw free body diagram for block A first. Okay, we now have the free body diagram of block A. Notice that my weight for A is shorter than the tension vector for the block A. Why? Because weight is trying to drag the block down, but the tension is pulling the block up, right? And it's way greater than the weight. That's why the block is moving up. Okay, it's always like that with forces. So now let us calculate. We'll start with block A, and we say Fnet is equals to ma. But since it's moving up, we will choose. Sorry, since it's moving, we have to choose a direction. Excuse me. So let's choose upwards as positive. Why am I choosing upwards as positive? It's convenient for me, right? Because I know the block is moving upwards. So why would I choose downwards as positive? You can choose downwards as positive, by the way, but you have to be very mindful. I'll show you why. So let me start with upwards. So if I choose upwards as positive, I have to indicate it here. Upwards is positive. Ooh, I forgot something crucial here. My summation sign. Yes, Fnet is equals to ma. Right, so now let me sum my forces. I have t is going up, so it's positive, plus I have weight, it's going down, so it's negative, equals to m. Acceleration, this block is moving upwards because it's block A. As block B moves downwards, it drags block A upwards, right? You should see that. So therefore, since my acceleration is also upwards, I will make it positive here. I won't change it. Now, however, if I had chosen downwards as positive, here's what would happen. My t would be negative because t is going upwards. Then my w, or weight, would be positive. When I get here, this thing is accelerating upwards, right? But I chose downwards as positive. So therefore, when I get here, I will do this. So you see, this is algebraically messy. I don't want that. It makes my life difficult. What if I forget to change this A? Because out of habit, maybe I'm used to just saying MA. So you see, always keep that in mind, okay? Choose the direction that is convenient for you. But at the same time, you are not restricted. There's no rule to choosing directions. It's all about what's convenient to you. Right. The only rule is never change it mid-calculation. Okay, let's continue. So I have transposed my weight and then I can now substitute values. This is mg, right? So weight, remember weight is mg. So the mass I don't know, so what we're looking for, and then the g is always 9.8. It's a constant. This gives me 13.68 m. Okay, so that's my t. Right, to avoid this whole thing of equation 1, equation 2, I could have started solving for t from block B. I wouldn't, so because if you see now, this is it's an equation, so I have to do equation 1. But to avoid this, I would have started with block B, because block B had all the known values. I would have easily solved for t, but it's fine. Let's continue this way. I'll show you what I mean. So block B, I choose downwards as positive for block B. Why? Because it's moving downwards. It's a convenient direction to choose, okay? So that's what happens with me. And then I have t pulling up, so t will be negative, plus the weight of B, block B, and then is equals to my m, A. A is positive because it's moving downwards, okay? So I transpose and then I substitute. Right, so now I want to find my answer. 7.5 times I get 102. Sorry, this is supposed to be a negative sign. And then I'm getting 44.4. So you see, if I started by solving for block B first, I would have just gotten 44.4 and equated to 13.68. So this is my T. So we know that these T's are the same. The tension in the rope is the same throughout. So we can equate 44.4 to 13.68 M. So we can say 44.4. 44.4 what? Newtons, okay? Never forget units, otherwise you will get yourself in trouble, even when you are a professional. So now we divide both sides by 13.8, and then we get 44. I get that my mass is 3.25 kilograms, which makes sense. Even from the diagram, it was literally implied that this block is smaller than block B. So this is the mass of block A. That's our answer, okay? So we are fine now. Let's check the following question. So now we want to find the maximum height above the ground reached by block A. I mean, if you think about this one, you might be tempted to say, well, isn't it common sense that when block B moves this distance until it hits the ground, it means that block A will ultimately, since block A was literally on the ground at 0, will ultimately reach the same distance and start hanging 1.5 meters. Well, that's true, right? That's very true. But the issue here is, as block B moves down, right, it'll obviously drag block A with it. But when it hits the ground, block A will not immediately stop, because this string is flexible. This is a flexible string. So it's not a rod that it'll just stop immediately. It's like if you have two cars towing each other with a rope. That's why it's not recommended for you to tow another car with a rope. If the rope is tight, these cars and this one is moving. This is the car that's dragging the other one. This is car B. This is car A. Car B is dragging car A, right? As car B is dragging car A and this rope is tight, they will move at the same velocity, which is what will happen to this block. They will move at the same velocity, right? But when car B breaks, it does not necessarily mean that car A will also break. Why? Because the string is not rigid, so car A will be able to move towards car B unless the guy in car A applies brakes. So it's the same with what will happen here in this situation that we have with the pulley, right? block B, as soon as it hits the ground, it doesn't mean that block A will also stop immediately. Why? Because block A would have gathered its own momentum up until that point. So it'll push slightly above the 1.5 meter mark. And then once it reaches its maximum height, it will then come back to this 1.5 meter and hang there. Okay, then everything will be at equilibrium going forward. So let me show you what it means mathematically. It means the maximum height that block A will reach above the ground is 1.5 plus x, no, not x, del y, or whatever, let's call it y, whatever distance above the 1.5 mark that block A will reach before coming back again down to 1.5, where it will then settle until we disturb it again. Okay, so we want this y so we can add it to the 1.5 and therefore find our y max, which is what this question wants. Right, so it's something that you had to think about, but that's what will essentially happen. Okay, and then yeah, let's see if we can find it. So I want you to note one thing. Okay, so since these two are moving at the same velocity, as soon as block B hits the ground at VF, right? Let's call it VF. When VF is equals to 3.41 meters per second, right? It means VA at that point will be moving at that speed, right? Until it reaches a peak height where the velocity is now 0. So only then will it come back down to the 1.5 meter mark. Okay, so what does it mean? It's like if VF for block B is 3.41 meters per second, it means if we want to find our maximum height reached by, this is block A, right? Reached by block B. If we want to find the maximum height reached by block A, we have to understand that its initial velocity before reaching that maximum height will be VI is 3.41 meters per second. Its final velocity, remember the velocity at the peak before this thing returns down, because it sort of loses momentum as it goes up. It loses its ability to keep moving upward, basically, right? Because now block B has stopped dragging it with it. So block B is just sitting on the ground. Block A moves up, and then until it runs out of that momentum that was propelling it upwards, okay? Which will then be our VF will be 0 meters per second. And at that point, it would have reached its maximum height. So let's find that. So from this information alone, I'm sure you can see that now we can use equations of motion again. Okay, so let's find it. I can take this. Right, so we have this information, and remember our acceleration is a constant 3.88 meters per second. Okay, so we can use our equations of motion. So which one can we use? We don't know the time it will take to reach its maximum height. So therefore, it means we must go back and use the very same equation, this one. So let's use that one. So we can say VF is VI squared plus 2 times our displacement in the y direction. Okay, now we can sub in our values. We'll have, so once you sub in your values, so from here it's just maths, okay? You can solve for your delta y by dividing both sides by 2 times 3.88. So you'll have something like, okay, I made a mistake here, sorry guys. So one thing I forgot to explain, our A, if you think about it, A, once the block, the block B, once it hits the ground, ultimately, since the acceleration A was being, the source of that acceleration was block B, but now block B has stopped. So what is accelerating block A now is no longer block B, right? So what I mean by that is it's now moving on its own. So the only thing that will accelerate it is the gravitational acceleration. But in that case, the gravitational acceleration, remember, is always acting downwards like this. Gravity is always acting downwards. So as this thing is moving up, gravity wants to pull it downwards. So A is 9.8 meters per second squared, right? But in this case, there's also an issue of direction, right? Remember, we said our upwards is positive for block A. And since our A is trying to move this thing downwards, we will make it negative when we plug it in here, okay? So then now you can substitute and you would have, you can make y, delta y, subject of the formula and solve. And you'd have something like minus 3.41. I like substituting everything and then just solving at the end, divided by 2 times 9.8. This will be 0.59 meters. You can say 0.593 and then round off at your final answer. Actually, let's do that. All right, and then that means our max, therefore max height is 1.5 plus 0.593, which should give us 2.09 meters above the ground. So this is what you would get. This was an interesting question, very, very interesting. Okay, so yeah, let me know if you have or you need more clarity. Okay, if you have any questions or you need more clarity, I'm always happy to explain. All right, catch you on another video.